Hi, welcome back to part two of the lecture on maximum likelihood. We're going to go over some, at this point, portion, we're going to go over some tricks of optimization. Previously, we've learned that with optimization, we can solve it with gradient descent, and we can also solve with a closed form solution, where you take the derivative and set it to zero. Okay? Now, when you do this maximization, there are actually some extra details you guys should be aware of. One of which is that if you are trying to minimize some kind of function, that's equivalent to minimizing some function times a positive number. For example, over here we have the blue line, which is just an equation for x squared. You can see that the blue line, the minimum point is x when x is equal to 0, right? And notice that if we were to multiply a number by the original function, the blue line, it becomes the orange line. The orange line, the curvature changes, the slope changes. However, the location where you get the minimum is still the same. It's still at 0, right? So this example, you can visually see that by multiplying a constant to a function during maximization doesn't really matter. So if you have a constant value, you can actually just get rid of it. Okay. This is why sometimes when we look at the regression objective, sometimes you see 1 over n f of xi minus yi squared. Other times you see 1/2, right? These constants, they don't really matter if you can find the solution. Okay, so this is what happens when you multiply by a constant. What happens when you add a constant? Right? It's exactly the same. Now, originally we have the blue line. If you were to add the blue line by 20, for example, notice you shifted the graph upward. However, the location that the x value that minimizes the function stays the same. Therefore, when you have a minimization of some function plus some number, well, in that case, it doesn't. You can just get rid of the number. Okay. The next trick is that for minimization, you're trying to minimize some function. Minimize, it's equivalent to minimize the log of that function. Okay. So alternatively, when you're trying to maximize a function, this is equivalent to maximizing the log of that function. Log the function. So you can see it here as well. We start with the blue line. And notice when you take the log, the minimum point is still the same. So nothing has really changed. So taking a log is a really useful trick when your function has e to the something, right? Because when you take a log or a natural log, then e disappears, and you all you have left is just the exponent term. All right. Also, when you're trying to maximize some function, that's equivalent to minimizing the negative of that function. So if you multiply by a negative value, so you start with the blue one. Notice how with blue, you're performing some kind of minimization. However, if you take the negative of this, it becomes an orange line. That exact same point is the maximization. This is the maximum point for the orange. Therefore, when you take the negative of it, you convert from maximization to minimization or minimization to maximization. You're like just changing it to the other one. All right. Also, we have a bunch of log rules that we have done previously. Log of e, this is the natural log of e, is equal to 1, natural log of e. Also, when you have a log of multiplication of 2 or 3 things, it's equivalent to log of x plus log of y plus log of z. And if you have division, it's equivalent to subtraction. You're trying to subtract the top one away from the bottom one. Okay, and if you have log of some kind of power of n, you will move that to the front. Like, or log of e, you just get x, right? Because the e goes away. Okay, so these are the tricks. Over here, for your next practice question, you want to practice solving maximum likelihood problem. Let's say you want to perform maximum likelihood, but this time you're trying to use maximum likelihood to find the parameters for an exponential distribution. So at this point, what you want to do is figure out what the IID joint distribution is that we want to maximize. So what is the joint distribution? And then figure out the objective, that the maximization problem we want to solve for maximum likelihood. Once we once we have it written now, use the closed form solution. See if you could use all these tricks. Specifically, use the log trick. The log, you want to make sure you use the log trick. The log trick will make your life easier. Use these tricks to simplify the problem and essentially find a closed form solution. You can find it. And this is where you take the derivative and set theta to 0. And when you do this, like, remember to use all the log property you have learned. After you've done this, then you want to remember from last class what was the theta we're supposed to have. And then how does our answer differ from what theta is supposed to be? So this is from last class. We know what theta was, right? It's 1 over the average. Okay? Now, in this part, in our maximum likelihood, if you were to take the derivative, set it to 0, then what would theta be then? Okay? And compare that with our last class solution. Okay. So over here is the solution. It turns out that if you were to go through all the derivation, which is what I expect you to do during the previous practice question, you would be able to identify that 1 over theta is the average. Therefore, theta is 1 over the average. From here, you understand why for exponential distribution, the theta is simply 1 over the expectation. All right, for your next practice, you want to load this file, and it consists of 1,000 individuals recording the time they first dropped their phone, okay, resulting in some kind of damage. The time is in terms of years, so a number 1.6 is equal to 1.6 years. And then what I want you to do is identify the P of X, first using what we learned last class, right? You want to basically get the histogram. By looking at histogram, figure out what the equation is. So that would be P1. And then once you know it, you can also solve the same problem using maximum likelihood and gradient descent. So use gradient descent, see if you can get the same solution. And then basically P1 is solved using the first method. P2 is solving what we learned today, the likelihood. And then what you want to do is plot out P1 and P2 side by side along with the histogram. P1 and P2 should look very similar to each other. Now the phone company you work for wants to know when is a good time to release the next phone. The manager has identified that the best release time is when 90% of the customer have dropped or damaged their phone. Based on manager's assessment, when would you recommend the release of the next phone? Okay, so you wanna go through this process. So this exercise here basically goes through the entire process when you actually work in the industry. First, you collect the data. So you collect the data about anything you are collecting. Once you collect the data, you either use the first method or the second method, maximum likelihood, to figure out the probability distribution. Okay. And then you want to plot it out so that you can make sure with histogram, make sure your equation matches the histogram. After that, then you can use this probability distribution to start answering questions. Questions such as when is 90% of the customer damage their phone, right? So you want to be cognizant of the steps we're taking. This basically every single step is what you might actually do when you're um, in a company or you're doing research. Okay, so make sure you can do this right here. All right, so now that we've gone through whole bunch of ways. We've done the histogram, which at this point is just providing a visualization. Um, and we've done that the second way, which is using them very often. You just look at the histogram, recognize the distribution, and then try to remember how that distribution's equation is most of the time mean or the variance. And today, so far, we've done maximum likelihood. Right? This is when you have an equation and you don't know what the theta value is. The theta value could be like anything. So you have to use an alternative approach, which today we learn is maximum likelihood. And the fourth method is what we're going to learn. This KDE is probably the most powerful method among all these. It's powerful because, one, you don't need to know P of X ahead of time. Previously, you need to kind of recognize the equation and then try to figure out the exact parameters in the equation. With K kernel density estimation, you don't even need to know what the equation look like. And second, it is very easy to implement and understand. So it's just an easy approach. The only downside is that it's expensive. So it's computational expensive. So you use up a lot of processing power. So this right here is what you want to know starting off with kernel density estimation. It's essentially another way to go from data to P of X. Okay, some kind of equation. Oh, another thing. For kernel density estimation can fit any shape. Any shape. Basically, you can have an equation, a probability density function P of X looks like this. Basically, any shape, KDE will simply fit it really, really perfectly. Okay, so let's get started. How does KDE work? How does KDE work? Well, kernel density estimation is identical to histograms. So if you understand histograms, you can immediately understand kernel density estimation. In histogram, you basically look at each sample and then you stack a block there. And then you stack another block. You look at two, you stack a block at two. You see three, you stack a block. So you can see by stacking blocks, the region that happens a lot end up stacking higher, and the region that doesn't happen very much end up stacking lower. And from this, you get the general shape of your probability distribution. So this is histogram, and like I told you, histograms doesn't give you a P of X. Right? Now, now KDE is doing exactly the same as histogram, except instead of stacking rectangular blocks, it's stacking a Gaussian distribution. So for example, let's look at this data set again. It's 1, 1, 2, 3, right? So what it would do is it would put a Gaussian distribution out of 1. And the second one is 1 again. Therefore, it will add another Gaussian distribution at 1. And then the third one is 2. So you will add a Gaussian distribution at 2. And then the last one is 3. So you add it. So this right here is P of X, right? So you're basically adding Gaussian distributions, and as you stack more and more and more, the numbers that are more likely will be higher, and the numbers that are less likely will be lower. Okay, now when you place a Gaussian distribution somewhere, remember the equation of Gaussian is 2 pi sigma e to the minus x minus mu 2 sigma squared, right? So basically, you simply by setting mu, you can put the Gaussian anywhere at the center. So 1, 1, 1, 1, 2, 3. So you will put the first Gaussian mu as 1, second one as 1, third one as 2, and last one as 3. Right? So that's how you set the mean for each sample of Gaussian. And you can also set the standard deviation yourself. So when you set the standard deviation, you can control how sharp it is. The smaller the standard deviation, the sharper it is. However, if you make the standard deviation larger, then you will look more like this. So what you can do is you can put your equation with various standard deviations and see how it matches the histogram. So if the histogram matches it really well, then it'll be great. So like this one, let's say if it's like this. So it's telling you that you want something smoother. So you want to pick something more like this. But if your histogram does look like this, then you want something sharper. So therefore, all you have to do is set the mu value at each point. So you have 1,000 points, you have 1,000 Gaussians. Okay, let's really look at this. So we have 4 points. And what I mean is the very first one is 1, right? Therefore, we put a Gaussian distribution center around 1. The second one is 1 again. So we add another Gaussian. Just like you add another rectangular block, right? We add it. So we add another Gaussian. And the third one is at 2. And the fourth one is at 3. So we're just adding all these Gaussian distributions together. And that's all. Now, remember, Gaussian distribution is a distribution. So the total area for this one is 1, 1, 1, 1. Right? So in this case, if you add all these areas together, the total would be 4. Now, we need to make sure it's a proper distribution. So we need to scale it back to this whole thing cannot be greater than 1. So we divide it by 4 to make sure that the total probability never exceeds 1, right? So this constant is just scaling it back. But the main idea is you are stacking a Gaussian. And when you add another Gaussian, it's equivalent to stacking a higher. And then you add a third Gaussian, it's equivalent to putting this and this one in. Okay, so KDE is super, super easy. Now, after you have identified the equation, there are 4 samples, therefore there are 4 Gaussians, 2, 3, 4. Right. You can imagine if we have 1,000, a million samples, then you're going to have a million Gaussians. And this is the reason why that is computationally expensive when you have lots and lots of samples. Okay. Now, now this is computationally expensive. So now let's say once you have identified this P of X, it's an equation. What you do when you have a X value, like you're trying to find a probability of X hat, for example, X hat. What you do is you plug X hat in here, in here, in here, in here, basically into every single one of the Gaussians. And then you add them together. This, once again, if you have a million points, then you have to do this a million times. Another reason why this could take a while to run. Okay, so this is the idea. Um, this plot here generates this kernel density. You This is from that data 1123. You can study this later for your own homework. And like I said, here's some data set that are actual real data sets. Notice how this is not a Gaussian, right? You can't use a Gaussian to fit this. So if you want to fit this data, you need to use something more advanced like KDE. This right here is also not a Gaussian, even though it looks pretty close. So, however, this you definitely cannot use a Gaussian distribution to fit it. So, like I said, with KDE, it is the method that can fit any, and I mean any shape, right? Any shape. All right, for the last exercise of the day, what you want to do is you want to write. So this code here generates this data, which it's kind of like a skew Gaussian. So what I want you to do is to generate the data, use the code here, and then use exponential distribution to see if it fits. It's and you're going to see that it doesn't do a very good job. Then you can try a Gaussian to fit, and you're going to see that Gaussian also doesn't do a good job. And then lastly, use KDE. KDE, you're going to see that the KDE, like this in the red line, does a great job. Right? It does a very good fit. And try to do it. Definitely try to do it first yourself. And if you're stuck, you're welcome to look at the code. So I think that's it for today. I will see you in the next class.